So this is for your notes. So I'm going to do a problem in a similar fashion like 19 through 22 in the homework. But this time I'm making my own example. Y equals square root of x equals 1, and I'm going to choose delta x to equal 1. The question is, by the way, delta x always equals dx, which in this case equals 1. Delta y and dy are different though. Compute delta y and dy for the given values of x, then sketch a diagram like figure 5 showing the line segments dx, dy, and delta y. All right, so first, let me go ahead and turn this way. So I'm going to show you how to get all those. So if y equals square root of x, that's x to the 1/2. Let's go ahead and figure out what dy is. So dy would be 1/2 x to the negative 1/2 times dx. Remember, it's the derivative times dx, which would be 1/2 times the square root of x dx. So there is dy. Now, what's delta y? Delta y would be, well, let me finish dy for the given number values. So 1/2 times the square root of 1, and dx happens to be 1 as well, which is big, but you know that's what I'm chose here. 1/2 times 1, which is 1/2. So in this case, dy equals 1/2. Now, delta y, if you remember the formula that I gave you, is f of x plus delta x minus f of x. Remember, I gave you 3 formulas at the beginning, and I highlighted them, and I said, go with these. So in this case, it would be f of 1 plus 1 minus f of 1. So that's f of 2 minus f of 1, which is square root of 2 minus the square root of 1, which would give you approximately 0.4. So notice here, for dy, I got 1/2. For delta y, I got 0.4. What do those numbers mean? I'm going to explain to you on a graph what the dy, show you the difference between the delta y and the dy. And really, this part right here, I should have done in blue as well, because that's part of what I did. The black above, this is all given to you. This is what I worked out, so I should have put it in blue. Anyway, so go ahead and write all this down. Then I'm going to show you what that 1/2 means on the graph and what that 0.4 means on the graph. And what the dx being 1 is. How are we doing so far? Are you guys kind of understanding this section? Madison, how are you doing? Okay.
I think my internet crashed for a second, but I think it's back now, so better.
Isn't this more fun than political science or German? No.
Of course, it's definitely more fun.
Well, definitely more fun than political science.
Sure. Yes, sure.
Yeah, go that one. Ooh, hold on. I need full concentration here, so you guys relax. I gotta make this square root of x graph count. Oh, yeah, nope. comfortable with that. Not quite as good as I wanted it, but I'm gonna have to do it. All right, that's good. So there's the graph for y equals square root of x. Now, the tangent line right here, that's going to be delta y. And let's go with another color here, the purple. All right. So here we go. When we calculated all this, going back to the math here, I said we got delta y to be 0.4 and dy to be 0.5. So that purple that you see right there, dy, that's 0.5. The delta y, that's the blue, that's 0.4-ish. And then the delta x and dx, that's equal to 1. That's what it shows on the graph. So you see how the red there, the red line segment, that gives you an approximation. Now, 0.5 is quite a bit far than, it's not that close to 0.4. That's because I made dx pretty far out there. See, the dx is pretty large. It's 1. So that's why the approximation is not that good. If the dx was closer, the red line and the black line would pretty much be almost the same. But because we went kind of further out, I can show you the picture. See how dy gives you an approximation, but the further you go and you make dx larger, this red line will get further and further away from the black graph. Here it's still pretty close. So at least close enough to show you the difference. Dy is that purple distance, 0.5. Delta y is the blue distance, which is 0.4. Does that make sense? You can see? All right. Now, you might not, on the problems 19 through 22, be able to draw the picture for all of them. That's fine, but at least be able to calculate the delta y and dy, okay? All right, now, let's do a word problem. It's not really that intense of a word problem. This is number 34 from the book.
Professor, sorry, quick question. Is that, can you move it up? Is that what's 0.4? Is that an X or a Y? Delta X or delta Y?
Oh, yeah, that's delta y.
Okay, thank you.
That's the blue distance. The delta x and the dx, that's the orange. And then the purple is the dy. Of course, you can't write purple in your notes unless you use purple. Madison probably used purple. She probably has all 32 colors.
I actually have a pen that has where you can push down multiple colors that I write notes
Oh
in.
yeah, I haven't seen those in a long time.
Yeah,
Is that like
and
4 colors?
yeah, and I don't know, it makes me really happy to draw things in different colors. So technically that's almost true.
All right. So what was I going to do? Oh, word problem now. This is number 34 from the book. So let me read the question, then I'll explain the problem. The radius of a circular disc is 24 centimeters with a maximum error in measurement of 0.2 centimeters. Part A, use differentials to estimate the maximum error in calculating the area of the disc. So here's what's going on for number 34. You have a circular disc, which is what I drew, and they're saying the radius is 24, but you measure it with some device that you can have an error rating of up to 0.2 centimeters. So here we go. So you, that's good, yeah. Okay, I'm gonna get rid of the graphic because it's throwing me off. Okay, so here's the radius, which is 24. Now, centimeters. But since you can have a maximum error of 0.2 centimeters, what they're essentially saying is dr is 0.2 centimeters. So r equals 24, but dr is 0.2. Don't worry about the units right now, we're just 0.2. So the question is, use differentials to estimate the maximum error. So first of all, to calculate the area. So area of a circle, the formula is pi r squared. So if we can possibly be off by 0.2 centimeters for the radius when we measure it, how much can we be off in the area? Well, more than 0.2, because the area, you're squaring the radius and then you're multiplying it by pi. So you can be off by even more amounts. So we're going to figure out what dA is, which is the differential of A. So basically, it's taking the derivative times dr. So 2 pi r times dr. Now plug in what you know. So 2 pi r is going to be 24. That's what we measured at. Dr is 0.2. That's given to us. So dA would be equal to 9.6 pi. And what is that in approximately real money? About 30 square centimeters. So pi is 3.14 approximately. So it would be about 30 square centimeters. So what that means is if you measure the radius of this disc, and you measure 24 centimeters, but the instrument that you use to measure it could be off by 0.2 centimeters, that means you could possibly have an error as up to 30 square centimeters for the area. Now part B, you don't have to worry about part. This is part A. This is all I want you to do. Part B, I'll put for you what's the relative error. Well, the relative error is delta A over A, which can be approximated as dA over A, which is what's dA? Well, that's actually pi r dr. What's AA? Pi r squared. So the pi's cancel out. One of the r's cancel out here. So we're left with 2dr over r. If we plug in our numbers, you get 2 times 0.2 over 24, which gives us 0.0166 bar over 6. That's the relative, which I'll explain what that is in a second. But I'm not going to ask this question like part B here on this first test. Then they also ask the part B, what's the percentage error? error is percentage. So that's definitely so you'll get 1.6%. So when I say this can be the area is this off by 30 square centimeters, well, is that a error in square centimeters? Well, depends what size this we're talking about. So in this case, percentage error is 1.6%. If we're talking about something the size of football field, 30 square centimeters is nothing. But if we're talking about something the size of a plate, like a plate that you eat on, well, then that's quite a bit of air. So it's all relative error. Relative error is the same thing. That's more than 1 percentage point. I'll just start doing that here. UR was given. Yes. All right. Anyway, so this is best I can. You want another example like this one right here? Well, I'm trying to do it. I want to cover you like that, which is really quick. It takes 15 minutes. You guys all got this? Okay. So if you remind me next time, I have another example that I can do like this, finding the dy and delta y, but we're going to move on here. Section 3.11, hyperbolic functions. We're not doing too much of this section. We're only covering this section, one section here, and you'll cover it in another one section that uses hyperbolics next semester. But you know your trig functions, sine, cosine, tangent. Those are based off the unit circle, where the hyperbolic functions are based off of hyperbolas. So when you see something that and the applications of hyperbolics, I guess they do come up in engineering once in a while. I'm not an engineer, but like if you read the book, they'll talk about the hanging wire problem where it uses a hyperbola. But we're just going to do some very basic stuff. If you see sin with an h after it, that means the hyperbolic sine of x. So it's not the same thing as the sine function you're thinking of. And you're only going to run into it right now here, hyperbolic sine of x. And that's equal to e to the x minus e to the minus x divided by 2. The hyperbolic cosine of x, sometimes a lazy person will call it the cosh of x, is the same thing but with a plus sign, e to the x plus e to the minus x over 2. And of course, the hyperbolic tangent is still hyperbolic sine over hyperbolic cosine, so it is this over that. So if you divide those two together, the 2's in the denominators cancel out, and you get that. Now, if you want to evaluate something like, hey, what's the hyperbolic sine of 1? Well, then you'd have to plug it into here so you can get your answer. And then you get the decimal approximation if you want. But we're going to go over the derivatives of them right now. So if I were to ask you, if we got y equals the hyperbolic sine of x, the derivative is, you'll never guess, the hyperbolic cosine of x. I could do this for you. You don't need to know this, but I could show you. So if you have y equals hyperbolic sine of x, since hyperbolic sine of x is e to the x minus e to the minus x divided by 2, I'm going to rewrite that as 1/2 e to the x minus 1/2 e to the minus x. I'm going to distribute that 2 underneath each one, so it's a 1/2. I'm going to tell you why its derivative is cosine. Now I'm going to take the derivative of each term. What's the derivative of e to the x? Itself. What's the derivative of e to the minus x? Also itself, but times the derivative of x1, which is -1. So there's already a -1/2 here, so -1/2 becomes +1/2, which that's the same thing as e to the x plus e to the minus x over 2, which ends up being the hyperbolic cosine of x. Now, there is some differences. So if you had y equals the hyperbolic, you know what, I'm going to write this in a better way. Starting right here. So if you have y equals hyperbolic sine of x, the derivative is hyperbolic cosine of x. If you have y equals hyperbolic cosine of x, the derivative is just the hyperbolic sine of x. It's not negative. It's not the same as the trig functions. If you have y equals hyperbolic tangent of x, the derivative is just hyperbolic secant squared. Now, these are all in your book. So if you go to page 261, it has the rest of them. Sometimes some of them are not quite the same. Like the derivative of secant is not secant tangent, it's negative secant tangent, hyperbolics. There's H after all of them. So here's what my suggestion for you. Do not worry about memorizing these. There's all 6 of them are on page 261. Go to page 261, read it, look at it yourself. Just have it, use it as a reference. So when you're doing the problems from 3.11, you can see what the derivatives are. Now, if that's not bad enough, not only do you have these 6, but you have the 6 inverse hyperbolic functions, like the inverse hyperbolic sine, the inverse hyperbolic cosine, and those are going to be slightly different. What you think might be a minus sign might be a plus sign, and so on. So that's page 263, like y equals the hyperbolic cosine of x. So in this case, the derivative would be 1 over the square root of 1 plus x squared, and so on. And then there's 6 of those. Those are all on page 263. So I would be telling you this even if we were taking an in-class exam. I wouldn't make you memorize any these 12 that we just did. I just talked about 12 functions. There's 12 of these. Sorry, there's these 6 right here, the hyperbolic functions, and there's the 6 inverse hyperbolic functions. I wouldn't make you memorize that even if we were taking a test in person. What I do want you to memorize, if you're going to spend time memorizing, is the 6 trig functions, like the ones that are based off the unit circle, and the 6 inverse trig functions, the derivatives of those. These, you don't need to memorize the derivatives of them. But when you're doing problems, go to page 261 and 263 to see what the derivatives are. And so let's do a problem so I can just show you how it's done. And once you refer to page 261 and 263 for the derivatives of these guys, and then you just do number 32, let's say, for example. Let's say I ask you to take the derivative of g of x equals the cosh of natural log of x. So what kind of function is this? This is the hyperbolic cosine function, right? Hyperbolic cosine of u. What's the derivative of hyperbolic cosine? Hyperbolic sine of u times the derivative of u. What's the derivative of u? One over x. Right? Derivative of ln of x is 1 over x. So, and then you got the chain rule and things like that. So on 3.11, I'm not going to, I didn't assign that much homework, just 31 through 41 odd, and that's it. I want you to more focus on 3.10, which is what we did majority of today's class, and also the related rates, what we went over at the beginning. So 3.9, 3.10. 311, just work on those. If you're not getting the answer, we can go over it. But keep in mind, the derivative of the hyperbolics are different. So notice, remember, when you did the inverse sine function, it was square root of 1 minus x squared in the denominator. This is square root of 1 plus x squared. The other one is much more important for you to remember, okay? This is not as important. It's like, I don't want to use a bad analogy here, but Olivia, can you think of a good analogy? No. All right, any questions? Any comments? Oh, Olivia, do you have any announcements before I give them a quiz?
No, we're good, Professor. Thank you.
Hey, do other professors cover hyperbolics a little bit more than I do? Probably, huh?
When I did it, we just kind of ran over it as well, and like I just saw like a problem on the exam and then never saw it again.
Okay. All right, sounds good to me. All right, let's take a quiz. I'm getting tired of looking at you guys. Just joking. Quiz number 4. So you want to take a 2 minutes to relax, catch your breath. Then I'll give you the quiz. I got to adjust the due time because I didn't think we were going to finish. I ran through those hyperbolics fast. Okay, I'll see you in 2 minutes. I'm just checking something on Canvas here. Hey, have you guys heard anything about next semester yet? I still have not heard anything.
I heard labs are going back and the smaller classes, but not the bigger ones.
Not even for like 3 times a semester for testing?
I'm surprised they're not doing like campus vaccinations or something like that, you know?
No, that's you go to CVS for vaccination.
I figure, you know, since students are wanting to go back to class, you know what I mean? Just to get that going.
Yeah, but the thing is, you got plenty of time till August to get vaccinated. The summer is going to be the same anyway. All right, so you got the due time is going to be at all right. You all ready for the quiz? So homework, you can do 310 and 311 and keep looking at the related rates in 39 until the answer keys for all the related rates are on Canvas for you. And we're going to take the quiz now. Ready? Desiree, what's your major, by the way? Did you say computer science as well?
Yeah, I'm taking it as a recommended course for transfer. But my major is engineering physics.
Engineering and physics?
Yeah, it's kind of like a hybrid major where it applies like physics concepts to engineering. So yeah, so it's kind of like the basis of all that. And I'm thinking of minor astrophysics as well.
Oh, what school do you want to transfer to?
I'm planning to apply to Berkeley in spring. That's when I should do everything. If not, if that doesn't work out the way it's planned, then UC San Diego is my
Mhm.
second choice. Yeah.
Well, what about Cal State Fullerton? No, I'm just,
I've always wanted to go to UC,
all
so
right, moving on. Yeah, I know. But actually, if you, but you're gonna finish, you got to take 152, 251 as well, right?
yeah. So I basically have all the semesters planned out, so I should be able to finish up by spring.
All right. Oh yeah, because we are in spring, so you got one more year at Fullerton College. Okay. Yeah. All right. So let's go. Quiz number 4. So you guys know the drill. Once you're done, submit your paper. Check your submission. Do not leave Zoom until you check your submission. But once you checked it, then you may leave. And I'll see you next week. Here we go. You don't have to write the directions, okay? Just the equation. All right, number 1, find dy or dx by implicit differentiation. So x to the 7th plus 5x y to the 4th plus y equals 10. Number 2, it's actually quick. Find the derivative. F of x equals natural log of sine of x plus e to the 3x. You get till 5:15. 16 minutes. But take your time. I'll give you a warning. Just FYI, number 2 is supposed to be pretty quick. You don't need to simplify it. Once you take the derivative, you're done. So you should be done in the next 5 minutes. All right, you guys, it's not that long of a quiz, is it? What are you guys still doing the math? You guys got to practice more.
I think we're overthinking the second problem.
Yeah, second problem is just one line and you're done. You don't need to simplify. You're taking the derivative of a natural log function. That's it. Well, time's up. You got to finish it up in the next minute and then you start scanning. All right, you guys, start scanning. It's already late. If it's too many more minutes late, I'm gonna take points off. So you're gonna lose points even more. All right, so I'm gonna end the meeting. So just turn it in and submit it in case